Physicists have known about electric charges and electric fields since the 1600s, and the gold leaf electroscope is a way of demonstrating them. You bring a negatively charged rod close to a metal platform that's connected to two gold leaves beneath, and when you bring it close, the gold leaves will separate. The reason they separate is because there's been a repulsive force because they both have the same charge. Now that's happened without the charged rod even touching the metal platform due to its electric field repelling away the electrons. So in today's video, we're going to have a look at all these topics on the right hand side, looking at field strength, equipotentials, Coulomb's law, and comparing to gravitational fields. So let's dive in. Now electric field strength is a definition that's very similar to gravitational field strength. It's defined by saying the force per unit charge on a positive charge at a point in an electric field. So we can define this using an equation. Electric field strength, capital E, is equal to F over Q, or force per unit charge, given in newtons per coulomb. Let's have a look next at some different types of field you can get. So we can come across uniform fields and radial fields. Now, unlike gravitational fields, uniform fields do exist in electric fields. They're not like an assumption because of the geometry of the Earth. So in a uniform field, we've got two plates parallel to each other, and the field has these kind of uniformly spaced lines between them. In a radial field, that's due to there being a point charge or a spherical charge with the fields pointing radially outwards. And the idea is that the field shows, or field lines show, the direction in which a positively charged particle or a positive charge will move. So in this diagram on the left, it's going to go down, be attracted towards the negative plate. On the right, it's going to be repelled away from my point positive charge. Now, because it's uniform, we say the field strength in our uniform field is constant, and it's given by the voltage, or PD, divided by the distance between those two plates. So an alternative unit for electric field strength is volts per meter, Vm to the -1. Now, we could also say this, instead of positive and negative, could just be a difference of 200 to 100 volts. As long as there's a difference or potential difference, this formula still works. For radial fields, we need to talk about Coulomb's law, which talks about the forces between two charges. And we assume they're point charges here, and if I've got one positive and one negative, they're going to be attracted towards each other. They're going to exert a force towards each other. So we defined Coulomb's law is defined by saying the forces between two charges are proportional to not just the charges themselves, but the product of two charges. So that's Q times by Q for the two different charges. It's also inversely proportional to the square of the distance between them, or the distance between them squared. Now, for point charges where there's negligible volume, that's just the distance between them. If they do have a volume, it's between the center of those two charges, or the center of masses of the objects. So combine those two relationships together, we get the overall equation. Coulomb's law is given by the two charges, Q1 times Q2, divided by the distance between them squared, and the constant of proportionality here is a little bit of a mouthy one. Now, it's 1 divided by 4 pi epsilon 0. Now, epsilon 0 is a constant. It's called permittivity of free space, and the number is given by 8.85 times 10 to the -12. Now, some courses will give you the value k instead, and say k equals 1 over that 4 pi epsilon 0, which is 9 times 10 to the 9. AQA doesn't. You've got to quote the whole thing, basically. So electric field strength is given by force per unit charge. So dividing that whole equation by charge, one of the Q's is going to cancel, the R squared is going to go to the bottom, and we have another expression for electric field, which is 1 over 4 pi epsilon 0, charge you're talking about, divided by R squared. Now, as charges can be positive or negative, that means that electric field strength and forces values can either be positive or negative. Now, that indicates they have a direction, so it means they are vector quantities. So they can point towards a charge or away from a charge, depending whether it's positive or negative. So that's a difference between electric fields and gravitational fields, which are only attractive. Okay, let's define electric potential then. So electric potential, similar definition to gravitational potential. It's only defined using this, which is to say it's the work done per positive charge, or per unit positive charge, i.e. 1 coulomb, moving a positive charge from infinity to a point. So the idea is, same as for gravitational fields, if it's going from infinity, that it's 0 at infinity, moving it into a point is going to be how we define gravitational potential. And the reason we do this is because F has to be 0 at infinity. F can't be getting bigger the further away you go, so therefore potential has to be 0. So to be increasing, if we talk about it getting further away, then it gets closer to 0, while increasing, meaning at 0 at infinity, it kind of makes sense of both those facts. So potential is work done per unit charge. Rearranging, it gives us Q times by potential difference. Similar sort of equation to gravitational fields, apart from Q instead of M. And we can also talk about equipotentials here. So equipotentials, we are talking about the clues in the name: equipotential, equal potential, points on a surface, or it could be a line, depending on if it's 2D or 3D, that link together places of the same potential. The idea is they're kind of similar to things like contour lines in geography, or on maps when you've got lines linking on a map the same places of the same altitude. This time it's just areas of the same potential. So when we draw these onto uniform fields, let's draw on our field lines between two plates, and let's give the values to each plate. Let's say one of them has got a voltage or PD of 400 and the other one is going to have a PD of 0 volts. If I was to draw on equipotentials, what it means is that at equal intervals, let's say halfway, we've got a potential of 200 volts. If I was to go to between there and 400, we're going to have 300 volts, and the bottom one is going to be 100 volts. Notice the shape, it's perpendicular to the field lines, and it kind of curves out at the end because the field lines curve out at the end for a uniform field. If I was to draw the same thing for a radial field, again, I've got my field lines going away from a positive charge. Now, keeping the same rules, they're going to be perpendicular to the field lines, and they're going to form, therefore, kind of concentric rings. Assume my field lines are a little bit more evenly drawn. Now, they get further apart the further away they get from a charge. Now, that's because potential is inversely proportional to distance. So meaning they can get further and further spaced apart, even for even intervals of potential. So using an equation for our uniform field, we can rearrange the one from earlier and say, well, potential therefore equals field strength multiplied by distance. For our radial fields, the equation for potential is equal to 1 over 4 pi epsilon 0 times by Q, the charge of the object, divided by R, hence where we get our inverse proportional relationship from. So combining the equation for electric field strength, so 1 over 4 pi epsilon 0, and we got Q divided by R squared, we can find the relationship between those two things. We can say the field strength is equal to the potential divided by R, or the change in potential divided by change in R. And that's known as the potential gradient. And we could be asked to work out from a graph. So let's have a potential and distance graph. And let's say potential is negative. We're trying to find electric field strength. We find the point, find the tangent at a point, and we'll work out the gradient, because field strength is Q over R squared, whereas V is Q over R. If I was asked to find the work done from a force distance graph, I'd find the area between those 2 points, or I could find the potential from that as well, because force times distance equals work done. So lastly, we're going to do a comparison, very quick comparison between gravitational and electric fields, because if you can learn one, you can kind of learn the other one, basically. There's a couple of differences. Gravitational fields can be attractive only. There's no such thing as negative gravity in our current understanding. Electric fields can be attractive or negative. For gravitational fields, they have positive masses, and electric fields, you can have positive or negative charges. But basically, every equation you learn about for electric fields, you can basically substitute out the charge, and you get the same equation with a different constant for gravitational fields, like Coulomb's law of attraction and Newton's law of gravitation. Field strength, we've got, I've done a capital E instead of a small case g here, equals F over M or F over Q, and potential is work done over charge or work done over mass if you're talking about gravitational fields. Now, gravitational fields, so learning the definitions and equations is really important. But also gravitational fields, you have your escape velocity equation and derivation, and you have Kepler's third law, T squared is proportional to R cubed, which you don't have an equivalent of in electric fields. So I hope you enjoyed the video. Here comes some exam questions based on this topic.